Thank you. Well, in the series of lectures, Eric Docker and Edward Witten have given us the precise description of superstring amplitudes together with a large proportion of the machinery that we are going to need to evaluate them. So maybe now we should try to do it. Yeah. So at least in some basic cases. So let me begin with the formulation that was given in Eric's lectures. So we learned that the scattering, the amplitude or scattering of massless bosons, n of them, is given by an integral of this kind. So in a rather recent, actually, formulation due to Edward, the integral has to be viewed, as we have heard, over a cycle. So a cycle which is a psi gamma, which is a thickening of the diagonal in the product of the reduced left supermoduli by right in the case of the superstring. And as we also heard for the heterotic string, which I won't discuss here, by the moduli space of Riemann surfaces and times the supermoduli. And for the notation-wise, we'll denote generically parameters for supermoduli for this cycle by MA and zeta A. Zeta alpha. And over here, we are interested in the scattering of n massless bosons. So that will require insertions of n vertex operators, V over here. And the integral will be over, again, some thickening of the diagonal of a product of Riemann surfaces. Now, what are these amplitudes that we have here? Well, first of all, there is this parameter P mu I, which was interpreted as internal loop momenta in Eric's lectures, which is a kind of pairing between holomorphic and anti-holomorphic forms, if you will. And the other part is this amplitudes from the left and from the right. So here, let me write down here the right amplitude. So it's a little bit heavy notation. So let's zero in on at least the most important piece of this at this moment of this expression. So in here, this quantity h sub a is a tangent space to supermoduli space. So as a runs over the dimension of supermoduli space, you can think about h sub a as a basis, right, for the tangent space. And hence, this quantity, which you can think of as an assignment of some number, right, given by a rather complicated procedure, admittedly, but it is an assignment of a number to a basis, can be viewed as a section of Berezinian. So due to that, this is the kind of things that we can integrate. Now, so in here, what you see then is that as a function of HA, you have this expression, which is a correlation function. And what it involves, as you can see, is some kind of expectations over fields which are written as XBC. And then there's this insertion here that depends on the basis H sub A. And there are these vertex operators. So we're going to try to figure out what are these things more precisely and how to compute with them. So that we'll develop techniques as we move along. So the first thing we would like to do is to write these things in components. Right? So remember that we have these fields which are x sub mu, and then capital B and capital C. And if you expand out in z and theta, this is the expansion of capital X sub mu. So there's a scalar field, and there is a fermionic field. And similarly for B and C. So here they are. And these indices, in some sense, indicate the weight. Now, what is their action? Well, the total action, right? So these are ghost fields. The total action is the matter field plus the ghost fields. And let's write it like this. Let's write it as one piece is the free part. So this is the free part is, as you can see, quadratic, right, in these fields. So this is the free action. And then there's this other thing which is a coupling of something that we call the supercurrent. Here is its exact expression. So it gets multiplied by this chi. Now, as you may recall from Eric's lecture, the chi is a way of deforming a Riemann surface into a full coordinate patch of supermoduli space. So the way we can think about this is the following. We are integrating over this cycle, but what are the parameters? On one hand, there's a parameter which is implicit because everything here is written with respect to a complex structure. So there's already a complex structure there. And then the other is this chi. So the complex parameters and chi form, in some sense, the basis of the coordinates of supermoduli space. And now the integrated vertex operator is given by this expression. So here there's one has this, right, it's a function of z and theta, right? And I would like to call attention to the fact that here there is a piece which involves this gravitino field, kind of z tilde. So it's the v is not exactly a 1-0 form, but really it has both components, 1-0 and 0-1. Now, how I'll describe calculation with these a little bit later, but let's now move on to the case that we are interested in. So we are going to restrict ourselves to genus 2, and here are some features that I would like to stress. The first is this dimension, right, that is easily found for genus 2. We know that the dimension is 3 and 2. So one feature of this is that the odd coordinates, right, there are only 2 of them, and any even expression will depend only to a single power of zeta 1, zeta 2. That simplifies things enormously. The next thing is that, as Edward explained at length today, right, that the supermoduli space or super-Riemann surface of genus 2 admits a natural holomorphic projection. And so this is going to be very helpful for us because we are going to use this projection in order to integrate out the odd variables. And so that's which is what I'm saying here. And how do we describe this thing here? Another way of phrasing it, right? This projection is not so abstract. It's very simple. The fiber over Riemann surface sigma is simply the space of all super Riemann surfaces, so super period matrices are equal to sigma. Right? So, all right. So this is our basic idea, and let's now try to implement it by making them a little bit more explicit.
What do you call
this may be an old habit from right, the super Riemann surface, super period matrix. Yeah, it should be just period matrix with new terminology. All right, so here I'm going to recall some very basic notions. The first is, of course, the period matrix Riemann surface. So we fix a canonical homology basis. We pick a dual basis of cycles, and the period matrix is just the periods of this basis along the B cycles. Now, how do we deform this to the period matrix, right, of a super Riemann surface? So what's going to happen is that from our point of view, because we are using this formulation of NSR, right, of the string where this chi appears, right, the way we're going to interpret it is we are getting a super Riemann surface by turning on this gravitino field. Right? So this is a derivation given by Edward a couple of years ago of the super period matrix, which is that if you start with a surface sigma with Berezinian of sigma, a local super conformal coordinates dz d theta. So if you turn on the gravitino field, right, the general section will become this, right? So dz gets deformed to this, and d theta gets deformed to that. And so now for sections of the Berezinian, holomorphicity will be equivalent to the form being closed. So the nice thing about this criterion is that it's in terms of smooth structure. It doesn't require complex structure. So we need to implement the fact that D of this new thing here is closed, and that can be worked out, right? And so what we obtain is that if we write the omega hat expand in terms of theta like this, we find that closeness, which is holomorphicity for the section Berezinian, is equivalent to this set of 2 equations, right, on the coefficient omega hat theta and the coefficient omega hat of z. So now if you look at these equations, actually, as Pierre also stressed this morning, right, these can be solved perturbatively by expanding in chi. Right? So one starts, for example, at chi is equal to 0. And you see that at chi is equal to 0, this simply means that these coefficients here are holomorphic. Right? And omega hat theta is a section of a spin bundle. Right? So this means that omega hat is a holomorphic spinor. Right? So if we are in a case of an even spin structure, we can assume that at chi is equal to 0, this does not have a solution. By contrast, this one here is dg bar acting on forms, so the solutions are simply at chi is equal to 0, the holomorphic forms. So from those, you can solve these perturbatively. And since you have nothing to start from the point of view of the spinors, you only have the solutions that you obtain by expanding in omega hat z. So starting from two holomorphic forms, you will end up with two holomorphic forms on the super Riemann surfaces. All right, so that's what we'll get, right? So this is what I was explaining. And now we can also associate to these sections Bresenian a generalization of line integrals, which in the presence of chi takes this form. So having this, one can then define the super period matrix, or period matrix, the super Riemann surface, by this same procedure. So from this point of view, it's rather easy to work out omega hat ij, because these omega hat I are perturbations in the odd variables of the holomorphic forms omega I. So one expands out and one sees this. So in genus 2, we don't need to go any higher, because typically the chi here, right, will parameterize the odd variables of supermoduli space. So there are only two of them, right? And so all expansions will terminate right here, right?
For all spin structure, what we can do?
Okay.
This is for even spin structures.
Okay.
For odd, you have problems. You have one more here that you generate from there, but then you have poles over there. So one. Okay. So explicitly, this is the formula, right? So if you wish, the way perhaps to interpret this that is useful for our calculations is that we start from omega ij, and turning on chi, we get this period matrix, which are given by this. All right, so now remember that our plan is to try to parameterize the fiber of super Riemann surface with the same period matrix. So how do we implement that? So you see that obviously if we start from omega and we turn on chi by itself, this is omega hat is going to change. So therefore, what we should simply do is that as we turn on chi, we should also move the metric on the G. On the complex structure. So this is the plan here, right? Right. So what we would like, we want to turn on simultaneously a Beltrami differential mu, and consider in this language the super Riemann surface that comes from, on one hand, turning on chi, on the other hand, deforming G to G of mu. So how do we choose G of mu? We are going to choose it in such a way as to keep our period matrix the same. Right? So this is the typical change of the period matrix under Beltrami differential mu. Right? So to first order, which in our case is exact, because mu, everything is of order 2 at most. So this is the deformation of due to mu. This is minus the deformation used due to chi. So if we want it to be the same, we should simply set this, require the mu be this.
You say you want to deform the metric, but it's only to conformal structure you want to
that is true. We want to only deform the conformal structure, and in some sense the Weil factor is an additional choice that we can pick. It will turn out to be irrelevant because of... in fact, in this context, there's also another thing which is not as harmless, which is that this condition in some sense characterizes only the cohomology class of mu. Or its conjugate. So one can add to any mu we pick a dz bar of a vector field. Right? So in some sense, by picking one particular mu, we are making another gauge choice. Right? So one more gauge choice that we're throwing in.
How am I supposed to interpret this formula? The right-hand side looks nilpotent because there's the chi's in it, bilinear in the chi, so it looks nilpotent. What's you're saying that setting that equal to the left-hand side, which...
Well, I write in practice, right? You expand this and you get a zeta 1, zeta 2,
yeah,
right, times the sections.
Yeah, so
and then you right. But then you also have a mu of z, which you will take to be zeta 1, zeta 2 times something.
Oh, so mu isn't...
Right, right. This is even, mu is also nilpotent.
Ah.
Right, right.
I see, okay.
Yeah, nilpotent. Right. So now here's a point which is a little bit slightly confusing. So as I mentioned, our chi is going to be viewed as a way of parameterizing our supermoduli space. So we are going to pick, typically we pick two sections, two generic sections, and we will choose chi to be this combination. Right? Chi is odd, so this is the only possible combination. And so, and then having this, we solve for mu, at least the class of mu, and then we pick mu as a gauge choice. And so then in our formula, then there is this particular choice of chi1 and chi2. And at the end of the day, of course, we want everything not to depend on that. Right? So you think about chi, and so within this, as long as you have chosen chi1 and chi2 and mu, then we have a formula where our coordinates are omega ij on one hand, and this zeta alpha, which are these coefficients of these things. So this is how we are going to parameterize the fiber of the projection, right? So keeping omega ij fixed, then the parameter is just zeta alpha. Now, so let's, what's going to be involved? So we have to pay a price for deforming the complex structure by mu. Right? Because, so the way that is, right, is again, as Eric also explained in his lectures, that here was the original action, right? The free path together with this supercurrent coupling to the gravity node. And now if you deform by mu, you will also get an additional term, which is the stress tensor coupled to mu. Right? And the stress tensor, here's the exact formula. This full stress tensor is due to the presence of all these fields, x, psi, cb, beta, gamma. But let me call your attention particularly to these components, which are due to x and psi, because these are going to be involved with our computations of vertex operators. Why these be part of the measure, which, as you'll see for this talk, I will assume as known, right, when time comes. Now, so there's this feature that Edward explained yesterday, right? And we see a manifestation of it in this context here, right? The feature that Edward explained was that to a holomorphic section of the Berezinian, there's actually corresponds a holomorphic form, and then plus an exact differential, right? So the same thing is going to happen here. So in our language is this: if you take a section omega hat, and on the super Riemann surface, which is g, mu, and chi. So very important that it not be g and chi. It should be g, mu, where you deform g. Then you can there exists the globally defined scalar function, so that actually integrating omega hat with respect to theta gives you a holomorphic forms. So that gives.
So you are using both vector field and minus 1 differential to deform the supercomplex structure.
Excuse me.
To deform the supercomplex structure, you use vector fields.
I use the Beltrami differential for the z.
You write this in terms of vector field.
Well, no. It's actually, it cannot be written as a terms of vector fields in general, right? Because if it were, then it would be equivalent by reparameterization.
Yeah, but I mean the local.
Locally, if you want to do.
So you need the basis for a vector field and the basis for minus 1.
Right.
Two poles, so you have 2g minus.
Well, there's this is Kodaira-Spencer approach, right, where deformation is a matter of changing scales on a fish. Yes.
So omega on the right hand side is a form on an ordinary Riemann surface?
Yes. It's a holomorphic one form.
So,
With respect to the metric of G.
when I wrote a formula like this, it was for a split super Riemann surface. Canonical.
Well, you start with this G at the beginning is split, right?
Yes.
Right, and then you deform it by chi and mu at the same time. Right? So now if you take the super holomorphic form with respect to this combined structure of chi and g of mu, then you can associate with a holomorphic form on G, the original. I think it's right. So it's this feature somehow that this is because at least in this NSR formulation that we're using, the holomorphic structure of the super Riemann is not as apparent. So it comes through in this way.
So
I try to interpret what you're saying as follows. We're making a smooth model of some kind of the super-Riemann circle.
Right.
And then the super one obeys a different condition from the original one, omega, but it has the same periods.
Yeah.
From omega by an exact form.
Right. Yeah, that's that's the exact form thanks to which you can compute the period and say it's independent. All right. So all right. So this is this effect, right, of deforming complex structure. And now, before I would like to go back and rewrite these amplitudes that we are supposed to compute, right, after carrying out all of this, right. But before doing so, let me stress a very something which is just purely technical, right. So it's just a computational device. Now, if you remember, right at the very first slide, there was this formula of gauge fixing that involves this formal expression, delta of the Beltrami differentials paired with the gauge field B. Now, the fact that this is delta is not so troublesome. It's rather that now that we are in the we are trying to deform both the G and chi at the same time, it means that the components of HA have both the Beltrami differential B as well as a change in chi. So due to that, this pairing here becomes kind of complicated. And if one tries to expand this, it becomes a huge mess. So there's a very simple observation, which is that instead of taking this, right, we can just replace it by a different set of Beltrami differential. Let's call it H star of A at the cost of introducing this ratio of superdeterminants. So in this ratio here, you see that it's independent of these so-called superholomorphic differentials of weight 3/2, the dual, if you wish, of super Beltrami differentials, and because you divide like this, and then on the other, it also independent of the choice of this HA and H star A. So one can make this change, and the very simple idea is that we can just pick, because this is arbitrary, we can just pick the H star to have Dirac delta function, to be Dirac delta functions. So they are supported only at points, and that makes these computations a lot simpler. And the cost of that is that you have to compute this correctly. So for example, one thing you can do is you can take the superholomorphic differentials which are dual to the HA, so that makes it automatically 1, and the formula simplifies to this, where it's understood that phi B has to be dual to the HA. So this is just technical, but it reduces this complicated thing to just correlation functions of these fields, B and beta. Right. And these are actually well known. So it simplifies our work enormously. All right. So let me now summarize the amplitudes that we have to evaluate. Because we are fixing omega ij, so when we integrate the d omega ij, and the amplitude is this. So as you can see, this factor here, right, is the one that from the previous slide, right, where we have made this delta function support. And then the others, this is this term Q of Pi, right, given by this, which was needed for chiral splitting, as Eric explained. So it's a little bit complicated, but it's just some integral with respect to this field x mu. And then here here's the vertex operators that we're inserting, where we're interested in the 4-point function. So there are 4 of them. And then this is the coupling of the supercurrent to chi, as well as the stress tensor to mu. So this is the whole formula, right? And now one thing that we have to be careful is that, remember that the vertex operator was a little bit given by an expression to begin with, and now due to this change of complex structure, these things have to be changed too. Right. So what happens that the new vertex operator is now the old one, which you can write it as V0, and then plus 2 terms, and one of them involves this chi, right? So chi is the effect of turning on this gravity node, and the other involves mu, which is the effect of changing complex structures. Right. So notice that they involve a dz bar, right? So from that point of view, right, since we are going to be interested in a holomorphic form, right, on moduli space, these at least pose some conceptual difficulties. Now, in here, though, also keep in mind also that you have your chi and mu, but chi is of order 1 and mu is of order 2, right? So sorry. So this is what the amplitude we have to compute. Right? So because the computation is somewhat long, let me describe immediately the answer, right? And then we discuss how to get there. So the claim is the following: that there exist the functions, right, which are scalar as a function for each j. These functions are scalar as a function of zj, and this amplitude that we have, at least after summing over spin structures. I should say that we tried very hard to do it without summing, right? But we did not succeed. It was just too complicated. So after summation, what we can say is that after that, then you have here, you have a piece here, which is actually the exact differential of this function s with respect to the missing variable zj. And the key thing is that this piece now is now a 1-0 form. Right? Because remember that this b delta here involved these vertex operators that had the 0-1 components, right? So they are not pure 1-0 form. Right? So we are simply saying that by getting rid of these exact differentials, they can be made a piece which is 1-0, and since these forms are closed, these will be automatically holomorphic. So now we arrive at something which is holomorphic, and in fact can be computed out exactly. And so the formula is something like this. It involves a standard complex function theory on Riemann surfaces. Here's the prime form. These are the abelian integrals. And then this is the period matrix paired with this internal loop momenta. So this is everything is holomorphic. And then this factor here it depends on the momenta, right, of the incoming and outgoing particles, and the exact formula is that the 3ys is given by this cyclic permutation, where delta z1 z2 is actually a 1 form in each of the variables z and w. So all of these things now end up being holomorphic forms of type 1-0 and can be integrated without any difficulty. So not only that, you see that interestingly also is that if you look at this H here, it doesn't depend on any of the choices we made. Right? It does not depend on the chi alpha that we use to parameterize super moduli space. It does not depend on the points that we inserted. Right? And it does not depend either on the particular choice of mu within its class. All of those choices, as one can imagine, they're all in these exact differentials. So since there was this issue about splitting internal loop momenta, we can see here a kind of a very simple example of how that works. So if you take the earlier formula here, where you have this holomorphic piece, right? Now suppose that we, as prescribed, paired left and right and integrate with respect to internal loop momenta. Then the answer turned out to be very simple. It's actually this produces the determinant of the imaginary part omega to the power minus 5 because we're in dimension 10. And then the rest is the Green's function, right? So times this Mandelstam variables. And so this is the so-called conformally invariant Green's function. This is the exact formula for it. But in fact, as Eric also explained in his lecture, because it differs from the standard Green's function by a sum of two independent functions, and because these momenta here add up to 0, you can also replace this one by that one. So everything is well defined. And this formula explains why one uses this chiral splitting, and that's why that leads to P. Because imagine that in a theory of scalar fields, your correlation functions will be given by Green's functions. And so when you have a formula like this, if you want to split into holomorphic and anti-holomorphic, you want to rewrite this under this form. So that's so altogether, this is then what we obtain, which is the final formula for the amplitude. Okay, so let's now try to, so this is the final formula. And you see that in all of this, forgetting about the exact calculations and what comes out exactly, the key thing is to make this exact form appear, right? And the hope that use it to cancel the rest. So I would like to illustrate a little bit that mechanism. Okay. All right. So now comes a slightly technical point, right? Before I had mentioned that we choose a gravitational field, which is a linear combination of two generic fields, right? So for practical purpose, again, it's convenient to choose chi supported at given by delta measures. So let's say there's chi is supported by is a combination of delta at Q1 and delta at Q2, right? So how do we choose Q1 and Q2, right? Well, actually, the notation here is not so good because before I had used Q alpha in the computational device, right? So right now these should be different. I should have written Q prime alpha. So sometimes one useful choice, which was very helpful to us, was to use the so-called unitary gauge. So these are the ones, right? This is the one that we are going to use. So that means that we want to choose Q1 and Q2 to be the zeros of a holomorphic form omega. So that cuts down a little bit all the gauge choices. In the end, right, we again don't want some dependence on omega. Right? Now, I just want to say a little bit comparing with other choices. Another very useful choice that we had used when we computed the superstring measure was the split gauge, where the points Q1 and Q2 satisfy the fact that the Zego kernel vanishes there. Right? Now, the advantage of that is that you can see that if chi is of this form, the correction from the period matrix to the so-called the period matrix, the super Riemann surface, is proportional to this S delta. So if this is 0, you have the advantage that the period matrices are automatically the same. Right?
It's not in the integration,
in
the expression for omega at S appear in the integral or no?
Omega
is defined like omega plus the integral.
Right, with the integral.
S.
Right, but then yeah, S is the Zego kernel, and chi in there, right? If you stuck in chi is equal to this linear combination of delta functions, it will pick out exactly S at Q1, Q2, at the two support. So that's why when this is 0, then the two are the same. So this is extremely convenient. But as you will see, and this has to do with the comment that I made a little bit earlier, which is that we did not succeed in computing things spin structure by pin structure. Rather, we had to take a shortcut by summing over spin structures. And if you sum with spin structures, the danger with this split gauge is that these points Q1 and Q2 depend on delta. So when you sum over that creates another dependence that we could not handle. So that's why we choose we're going to choose the unitary gauge. So now, of course, at first sight, it looks like the unitary gauge, right? Right, they are by definition independent of delta, but you may fear that the Beltrami differential is still dependent on delta, but that's not the case. It turns out that you can write it by factoring out this S delta. Mu is at times a mu tilde, but this mu tilde is independent of delta. So that will simplify things enormously. And now the second issue, which is why the notation here I was careless about this, is that remember that I had used these points a Q alpha in order as a computational device. Now there's a second set of points, let's call it Q prime alpha, which are the supports of the chi. They're not the same. Right? And it's tempting to set them to be the same. Right? Now, usually when you do that, there's always some danger because you are supposed to pick generic slices, but it turns out that one can show that it will be okay. Right? So you essentially, because everything is independent of the Q alpha in our computational device, so at the end you can let them tend to the support of the gravity. All right. So now let us begin the calculations. Right? So let's organize the evaluation of these in the following way. Right. So the first thing is that to determine the so-called superstring measure. Right. So superstring measure is the one where you don't have any insertion of vertex operators. No, none of these V's. Right? So that means that if you look at the formula, right, we don't have any v's, and we just have this term here that came right from the from our computational device, and this is simply the insertions of the internal loop momenta as well as the deformation by chi and mu. Right? So this is the first thing that we have to compute, and so we computed this using this formalism, right? And we found it to be right. So this d mu consists of two pieces. One which is independent of zeta 1, zeta 2. The other is of order zeta 1, zeta 2. So let me discuss first this mu 0 here, right? So this is the one independent of zeta 1, zeta 2, and here is its exact formula. So right. So what it is that you can write it as a standard measure omega ij times a factor, which, as I mentioned, one can compute explicitly in terms of standard function theory on Riemann surfaces. I would just like to call attention to one particular point. It's rather easy to see that this whole combination here is independent of the choice of the points P. Because the BPA here gets cancelled with these two forms evaluated at PA, but it's not going to be independent of the Q alpha, right? And as you can see from this formula. And this is not, in fact, if you deal only with the partition function and no vertex insertions, you will end up integrating with respect to zeta 1, zeta 2, and of course this part here will not contribute. However, as you will see, when we introduce vertex operators, right, this will play a big role, right? And it's very important that this dependence on the Q alpha cancel the ones from the rest of the correlator. In another issue, which is what Edward mentioned in his lecture earlier today, is that near infinity, one has to have a correction to this procedure, right? It turns out that this correction, right, the bottom component, d mu 0, plays a big role. So it's very important to have a formula for it. Now, so the top component of the measure was found to be this formula, where the key new ingredient is this form that is called Z6. So this is a standard modular form. This is theta to the power 4. And then Z6, there are now many, many ways of writing this. Many people in this audience are experts on that. One way is to write your spin structure even as a sum of 3 odd spin structures. And this is a way to write it. As you heard today, we did not get, hopefully, I'm not sure I will get to hear it, but Edward obtained another derivation of this d mu 2 using purely holomorphic methods, a super Mumford form. And he got this beautiful formula in the hyperelliptic representations, and where the inverse volume, right, was defined to be this, where you just take away these 3 forms, and then this can be checked to agree with that. However, we are not going to be busy so much with deriving the measure for this talk, right? So let's concentrate rather on the effect of these vertex operators, right? Not so much the measure, but the 4-point function. So when one computes them, let's divide them into different groups. So what happens then is that you see that in the B delta, right, in this you have these vertex operators, right, together with the Q, and then together with, as you may recall, the exponential of the supercurrent integrated against chi. So now if you expand that out, because we are again have only 2 odd dimensions, right, the most terms that we get will be 2 factors, this chi times the supercurrent. Another is 1 factor. So if we regroup it, these are all the terms that will happen. The first one is when all the contractions of our vertex operators are disconnected from the ones of the measure. So this is the case where you simply have this the vertex operators multiplied by the top form of the measure, and then the other is when there is some contraction of these vertexes with the other parts, and this is what they would look like. Right? So you have all these Q's here, and now there are terms where the two supercurrents appear. There's the terms where the stress energy tensor appear, and then there are terms where there's these corrections to the vertex operators. So this is the set of 5 corrections. Now, let me just mention, just so that we can see very quickly what's not going to contribute. I just want to say that in all these expressions here, all the fields are free. So we are just taking weak contractions, right? So nothing more complicated than that. And the standard weak contractions, you can understand it from the point of view of Gaussian integrals. Right? The Fourier transform of this Gaussian is this other Gaussian with inverse, and hence by differentiating, you see that any moment here can be written in terms of products, right, of terms from the inverse of the matrix. So these are what we call contractions, and you see that what it is that we are, whenever we contract, we are taking 2 indices from here using the inverse matrix, and then we pair all possible pairs. So that's a simple rule. So this, of course, is a trivial thing in the case of finite dimensional integrals, and we just take as analogues of that the case of free fields x plus, where the operator here is, roughly speaking, the Laplacian, and then this is the inverse, is the log of the prime form, and the same for the Szego kernel. Right? So where you have psi, then the contractions are carried out with the Szego kernel. So we simply will compute our correlation function using this the prime form and Szego kernels. Now, because the thing is a little bit messy, it's very important, in fact physically also important, to organize these into kinematic invariants. So a vertex operator depends on momentum as well as polarization vector. And so one defines this Fi mu nu, which is the field strength of the ith particle. And then one forms also these various invariants obtained by contracting these in a cyclic manner, all the indices. So, and then let's define these 2 big kinematic factors. One, let's call it K, and the other one is C. K is totally symmetric in everything, while C is anti-symmetric, right, in pairs. Right? And let's try to group our answer in terms of these. So let us begin with the first evaluation, the simplest. The simplest is that, right, we are dealing only with so-called disconnected. So that means that all the contractions here, these are the vertex operators, right, of type of the leading type, because we already have a d mu 2 here. This is the top terms. So therefore, we only keep the leading type. So we need to contract this, and so the claim is that the only contribution will come when you have, so to speak, the full 4 fermion bilinear. That means all these bilinear here, all 4 of them. Right? And the reason for that is that whenever it's not all 4, that means there are only 1, 2, or 3, with the others being contractions of the fields X with another field. And so when you contract only 1, 2, or 3, what you're going to get is this. The factor d mu 2, as you may recall, contributes this factor of Z6. And then the contractions of this of the field psi here will either produce the Szego kernel to the square, or a cyclic grouping of Szego kernel like this. And it turns out, right, that one can show by simple identities that all of these are 0. Right? So that means that the only contribution is from the full 4 fermion bilinear. Right, all 4. Now, how do we compute that? Well,
don't we have to worry about contractions with the psi's which are in the PCRs, the picture changing operators?
the psi.
Or will that come later?
Those usually involves a chi, right?
Yes.
And here we are dealing with the disconnected terms. So that's d mu 2 is already top rank. It already has a zeta 1, zeta 2.
Okay.
So these are what you mentioned will come later. They'll be. So then the correlator says, so now for W, if you have the full 4 fermion bilinear, right? Then not surprisingly, now you have 4 Zego kernels, right, in these identities, and this time they will no longer produce 0. Right? So one can establish an identity involving these delta, and they produce right up to this factor of modular form psi 10, precisely these pairwise holomorphic forms that arose in our final result. Now, if you may recall from the formula, in our final result, we don't see the kinematic invariant C. Right? We only see the kinematic invariant K. So in fact, these will cancel. But we don't see it as yet. Now,
is that combination of deltas completely symmetric in Z1 up to Z1?
No, it has the symmetry of this C1, 2, 3, 4. I remember that C1, 2 here is symmetric in 1 and 2, anti-symmetric 1, 2, anti-symmetric 3, 4. So the whole combination is symmetric, but each piece is. Now, evaluation of Y1. Right? So here's one example where these are picture changing. Right? You have chi times the supercurrent. So now in our formulation, remember that the chi is supported at delta function, and the supercurrent involves psi plus times dzx. So this produces 2 psi's, which when you contract, either they end up contracting between each other, producing a Zego kernel S delta Q1, Q2, or else they contract with the fermion, the other fermion bilinear in the vertex operators. So that means that they produce things of this kind. So the ones that are 0 are this. If you just have S delta Q1, Q2, it produces 0. Right? And same for this. And so once again, as long as you don't have the full 4 fermion bilinear, everything is 0. And the only ones which remain are when you have them all here. So there are 5 of them, but you have a Q1, Q2 coming from the supercurrent, and these are the 4 fermion bilinears. And these are in some sense the first hard identities that we have to prove because they don't give 0. And in fact, they give, right, they give this form omega zi, where you remember that omega is the holomorphic form whose zeros occur at Q1, Q2. So if we use this formula, it's rather easy to expand and plug it in, right? And and so this is what we would get. Right? So this is the one involving 2 chi's. Now, there is one which perhaps this is the most difficult one, because the Y2 is the contributions that is due to the insertion of the stress tensor. So for our purpose, it's convenient to break these into 2 parts. You have the stress tensor due to the scalar fields and the stress tensor due to the fermionic fields. And so these ones is easy because their contractions don't depend on the spin structure. And when you work it out, this is what you would get. Notice, however, that there's one complication from here because insertions of the stress tensor involve an integral against the Beltrami differential. So here it is. Now, for the contribution of the fermionic stress tensor, right, you see then that you will have contractions of psi plus, but also contraction of dz psi plus. So you can recognize that this is the kind of fermion stress tensor insertion that will occur in this formula. Right? So you take this, then you have psi s here coming from there, and then the derivative of this. So then let's write then the contribution of the fermionic stress tensor. So here they are, right? This is mu times the fermionic stress tensor, and these are all the fermion bilinears, and one can compute them out, right? So it turns out that it's a kind of complicated formulas where this time both the C and K appear, both kinematic invariants appear, and they are given by coefficients of this kind, right? So the coefficients, right, there is, here's the formula, right, which is involving the key thing involving mu against this fermion stress tensor insertion, right, and then there are various combinations, and the key thing is to have to evaluate this, right. So it turns out that, and here's the key thing where this function lambda of z appears. Remember that we had chosen our points q1, q2 to be the zeros of a holomorphic form omega. And the mu tilde depends on that, because mu tilde is used to solve for the corresponding corrections. So it turns out that this thing here is exact. It is d bar of a globally defined scalar function. And we find that after computing this I, for example, the symmetric IS is equal to dz of lambda times omega of zj. So this is now a pure 1-0 form, which is a D exact. And for the this is the symmetric one. This is the anti-symmetric one, which is simpler. So this allows us to solve to find the contribution of white tube psi, the contributions of the Fermionic stress tensor. Now, and here I wrote it down more carefully, right, in full, collecting all the terms. So you have one term involving this kinematic invariant K together with the partial derivatives of lambda with respect to Zi, right, for given variable Zi. The rest here, right, is holomorphic in Zj, so J different from that. And then it's again, this time it's not too difficult. One can compute the contraction of Y3 and Y4, which are contributions of these corrections to the vertices that only involve chi. Now the key term, right, that one has to compute is Y5. Now Y5 is simply the contribution to the whole amplitude of this of the corrections to the vertex, which is due to the deformation of complex structure, right? So in fact, it turns out to be given pointwise by this sum of mu tilde j, right? And then the rest is this. So let us now try. So we have now computed all 5 of them, right? And let's now try to put things together. So so if we combine all the terms, right? So the interesting thing, one is that you remember that this B delta disconnected, right, depended on this particular kinematic invariant C1, 2, 3, 4. And if we look at the contribution of the fermionic stress tensor, y psi here, then we find that these two actually cancel. Now the next one is this. I'm sorry. This should be yx. I'm sorry, not y psi. Yx. So y psi, right? Oh, I'm sorry. This is the C piece of y psi, and this is the K piece. Remember, they were proportional to these two kinematic invariants. And if you take the K piece, it turns out that you combine the K piece with the Y5 piece, right? Then you can write it under this form up to an exact differential. Because remember before, right, the term that appears was the derivative of d lambda. So if we can complete that into a full exact differentials. And remember that in our formula, we allow ourselves to discard exact differentials. Differentials which are exact in one variable and holomorphic in all the others. So that means that these two things here, discarding this, can be replaced by this. So now if you take this piece here, which I'm reproducing down here, and you combine it with the remaining contributions, namely y1 and y2x, you find that all gauge choices cancel. And one arrives at this expression, right, which was the one for the holomorphic form that I had mentioned. So this is how the calculation goes. And let me just add a few words about these identities, how they come about, right? So there are identities of, I should also say that all of this, as explained this morning and this afternoon, the odd spin structures don't contribute, right? So all these identities are summations of even spin structures. And what happens is one has to combine either the Riemann bilinear identities or the Fay tri-second relations, which is bosonization, right, in the formalism of physics. And there are, however, a few identities involving the most complicated ones, for which we were able to do it only through the hyperelliptic representations. So that makes them a little bit more difficult to generalize. But otherwise, the moment you know the answer, it's not difficult to try to prove that. So maybe I just stop here. I know there's a talk coming very soon, right? So maybe, okay. Thank you.
I just want to make a remark that what I find remarkable about the answer, although not in the form we're seeing here, but in the form that Eric was discussing yesterday.
Oh, okay. Yeah, I can go back to that very quickly. This one.
Well, yes, okay. So that version of the formula is written as an integral over moduli space, but for each point in moduli space, an integral over 4 copies of the curve.
Right.
So if we had a nice splitting of M2 and 4, then by integrating over the odd variables, we get a formula roughly like that. I wouldn't be totally surprised if M24 is split as long as you require the points to be distinct. But to get a nice formula like yours, one would need a nice splitting, not just some splitting. And I can't imagine a nice splitting of M24. I also, I feel that such a nice simple answer should have some kind of slightly
easier derivation. Yeah.
should be something, maybe a clearer explanation of why there's in the end a nice formula. And since M2 itself is split, as you used at the beginning, it's clear that when you integrate over the 4 points, you get a relatively natural formula. But it's very surprising to me that before integrating over the 4 points, you have a nice formula.
Yeah, it's. I was thinking about, suppose instead of looking at the fiber of preserving a period matrix, can one look at the fiber preserving perhaps a period matrix and integrals between 2 points, between pairs of points? I guess we
discussed that.
Discussed that, right? Yeah.
Well, it's not totally sure that it's wrong, but.
Yeah.
Questions? Lovely, thank you, Mr. Berger.